Okay, so thank you everybody for coming. We are very happy to have Davide Bacciu as a guest today. Officially, this is a seminar, a conference for the Scuola Superiore, and so it's open to actually anybody. But we have a number of messages on the chat that are for people that need to be recognized as participants to this. Let me first of all thank Davide Bacciu, who's a young and very active researcher in the field. Being young is not a merit, but being very active it is. And we hope we will be able to exploit this feature. I still have people that want to enter. Okay. I believe that he is very open to interaction, so please use him as best as you can. And let me also remind you that this meeting is going to be recorded. There will be another meeting tomorrow at the same time, 2 hours, and also that one will be available on the web. And thanks again to Davide, and please go ahead. Thank you.
Thank you, Alberto, for inviting me over. It's a pleasure to be here, and it's a pleasure to be with you. Good morning. And I'm certainly open to interaction. Actually, as I anticipated before the official starting of this lecture, I have a fairly oversized slide deck, which I see as an opportunity rather than a limitation, meaning that we can sample for it also based on your interaction. The overall idea of this lecture, seminar today, is basically to compress what I typically teach in a semester into one slide deck. So probably not going to work like that. And whereas instead I can really go to points where you are more interested into and aspects that you're more interested in. I built it like that because I know there is an heterogeneous background here. So, but with the general scientific, strong scientific support. So I also can go deep dive into technical detail if you'd like. Otherwise, I can take it more on the methodological side, presenting fairly interesting models and their applications. So please interact with me so that I understand what are your interests and I can tune the presentation. So a couple of preliminaries, just so that first things you know who I am. I'm an associate professor at the computer science department in Pisa, where I basically work on machine learning since a couple of years. Thanks for addressing me as young. I'm not that young, probably. I've been working on neural networks since 2003, basically. So it's quite some time still. So I work on development of models based on theoretical questions, based on application questions. That's basically where I get my inspiration for the work. I coordinate a fairly large number of PhD students, and we do have a machine learning group in Pisa, which is called the Computational Intelligence Machine Learning Group, and I'm part of that since 2003. I also recently founded a laboratory on pervasive AI. You find the link there if you're interested, who deals with the aspects of AI as a pervasive technology and how you can support that from computer science and ICT points of view. It's a fairly big group. It's 60 members, and we do have quite an amount of active projects. I myself coordinate a European project on pervasive AI, and I operate around a couple of scientific societies. One is of particular interest for what I'm going to be talking about tomorrow, which is the task force from the IEEE Computational Intelligence Society. It's a task force on learning for structured data, basically learning for graphs, trees, and the sort. And it's interesting because tomorrow we're going to be talking a lot about deep learning for graphs. And I'm also the secretary of the Italian Association for AI, which I strongly invite you to check over if you're interested in AI. If you're a student, you have good fares for joining the association, which also offers scholarships, funds for attending conferences, and also as prizes for master students and PhD students and the research work. So check it out. And that ends the part about self-advertisement. Let's talk about today. As I anticipated, this is basically intended to be a super condensed lecture. As I don't know what's the background fully here, I've started it with a refresher of machine learning, basically the concepts, okay, so that we have the same terminology when we speak. And then we go on with fundamentals in neural networks, starting from good old perceptron, and then going up and up, or deep and deep, if you'd like, to deep learning. And of course, being a restricted amount of time, what you're going to be getting is a fairly biased view of deep learning. So my view, I'm going to be trying and arguing and producing, and the idea here is to generate discussion around my personal view of what's deep learning. Okay, and what I'm going to be doing is, well, avoiding images basically, and talk about deep learning as a representation, basically as representation learning. In order to do that, I will use autoencoders as a case study. And after that, I'm going to be slowly moving towards the structured word, introducing the first form of structured data, which is sequences, of course, and using it as a good thing, let's say, as something to introduce recurrent neural networks, their problem, their issues, and how we got past them. And here, now and there, I'm going to be introducing some spot research, interesting research ideas, research questions, recent research connected with what I'm presenting. And of course, that will be biased as well, because it's my personal own selection of what I feel it's interesting. So let's start with these fundamentals of machine learning. And again, I honestly am going to be going slightly quick on this one, but you do stop me, scream, yell, do raise hands, whatever it is, to attract my attention if I'm being boring, if I'm being too quick, whatever it's that you feel that needs to be changed in my way of delivering this seminar. So the first question one might ask is, what's AI versus ML versus ANN versus DL? Okay, so what that might be the kind of reaction people get when you start delving into those kind of acronyms and you don't know what's the relationship between those. So let's start by cleaning up things, okay? What's the relationship of deep learning with the rest of the world of AI? Let's take supervised task as a case study. Okay, so here the task is given an input, output a prediction. So classical diagnostic task. I want to create a synthetic clinician that receives inputs about a patient, outputs a diagnosis about the patient. Okay, the way in symbolic AI, what was the predominant AI up until 2012, possibly, did that. The job was basically to take the poor old clinician, chain it to a chair, torture him until he got out all his reasoning or a reasoning, and outcode that reasoning rules along with the knowledge that that needed to go along with that into a rule base or a system that could be run on the reasoning that can basically implement within the computer the reasoning of the clinician. That requires, of course, a lot of leveraging the humans. Machine learning, what attempts to do is attempt to leverage the data as well, and it's a subset of AI, as you see there. And well, there what you have is a trainable predictor, which basically outputs a diagnosis based on something that it has learned, the diagnosis that is learned to output based on samples, data examples. Okay. The trick here is that much of the work in the classical machine learning setting, in non-neural network setting, it was about engineering features. So taking very noisy data, transform it into some engineer data so that engineered data was cleaner, nicer, smoother to be fed to a trainable predictor. Okay, so a lot of sleepless nights of feature engineering. So people chained to the chair are now engineers and no longer clinicians. Then there is the world of artificial neural networks, and that is a world in which you would like ideally to learn those features, to take the feature engineering engineers out of the loop, and have the learning model itself learn to represent the data. Okay, that is where I first start introducing my personal view over deep learning. It's not only my personal one, my view over deep learning. Neural networks are basically about learning how to adaptively represent data that is as raw as possible, as complex as possible, without having the human in the loop of the information representation. Classical artificial neural network attempted to do that one shot. Okay, I have one layer. I want that layer to become my universal layer that knows how to represent input noisy data into a good, nice, clean form that then feeds into an output layer that does the prediction. What deep learning does, it's basically saying, yeah, you know what, that's not a very effective way of attempting to learn a good representation. A good representation can be learned in a pipeline. Why? Because you first want to learn a slightly more refined representation of data at the lower levels here of the hierarchy, and then you incrementally refine in more abstract representation of information up you go in the hierarchy. Okay, so that has demonstrated to be more effective. It's more akin to how the brain works, by the way, not that biological likelihood to make any sense right now in deep learning. But yeah, you know, if the brain works like that, possibly that there is a reason that of efficiency and efficacy. So that basically works well. Okay, theory tells you otherwise. It tells you that in theory, a single layer, multi-layer perceptron with an infinite number of neurons is capable of representing any function. Yeah, but then you need to train it. The fact that it's capable of, and it's not, doesn't mean that it can't actually learn it. So there's a big issue there. And as you see, I draw the deep learning dashed box going out of the artificial neural network field because it grew as a subfield of artificial neural network, which is a subfield of machine learning, which is a subfield of artificial intelligence, but it has outgrown artificial neural network. And now deep learning is something that encompasses different paradigms in machine learning because it puts together neural networks, statistical learning theory, as well as probabilistic models, for instance. So, and we're going to be seeing examples of that in a presentation. So just to be on the same page, when we talk about machine learning, we typically talk about 3 types of learning tasks and associated data that you need in order to fit them, because we're talking about the data-driven world. One is supervised learning, basically the one that we saw before, given an input, produce an output. Okay, classical problem of function approximation. Okay, I'm not spending much time here. Again, if you have questions, just stop me. As you note, I tend to speak fast, so if you want me to go slower or whatever, just scream. Okay. Another task is that associated with unsupervised learning. Unsupervised learning is about making sense of a data sample. Okay, there is no supervised information, or there might be some weakly supervised information. There is a whole word in the middle of the two guys. Okay, there is weakly supervised, semi-supervised, whatever supervised. But let's focus on the major categories. Okay, unsupervised learning is about making sense of data, which means understand, in a way or in another, understanding the structure of the data. You don't have supporting information in the form of these examples should be going into this partition, into this group, into this into this. It has this nature. No, you don't have it. You want to discover that. Okay, so that's where clustering fits and many other task feeds, but basically at the higher level, what unsupervised learning is doing at an abstract level is possibly understanding the distribution that generates the data. Okay, that's what you would like to do. Characterizing the data possibly down to the point in which you learn something that is an approximation of the data generating distribution. And then there is reinforcement learning, and not completely sure there is a subset of machine learning. It's possibly something that goes outside of machine learning as well, game theory and cognitive sciences and so on. But yeah, it's still connected with machine learning. The community is almost the same. And there, what you do have is typically an agent that is interacting with the word and is taking decisions about the word, and it's receiving from the word, from the experience that is performing in his interaction with the word. That can be physical, virtual, doesn't matter. It's experiencing rewards. So you're doing good, you're doing bad, basically, or how much you're doing good, how much you're doing bad, and based on that, on those rewards, is attempting to find out what are the actions, the best actions to be performed. Okay, so it's not supervised learning because the word doesn't tell you what actions you should be performing. Okay, that's supervised learning. There is no teacher here. There is only the bad word that eats you if you do bad and provides you with rewards if you do good. Okay, but you know, modern machine learning is far more than that. It's about taking data, understanding the data, reasoning about the data. So attempt to encode into learning models, reasoning processes, explaining the learning models. So how a learning model reasons itself in order to explain it to the human, because you can't take something that makes a diagnosis and throw it at a clinician and expect the clinician to use it unless you explain how the hell the black box is taking decisions. But there are other tasks that exceed classical supervision that are dealing with the generation of new data. And that is intimately connected with the understanding and learning the data generating distribution if we connect to unsupervised learning, because once I have the data generating distribution or a sampling process over it, I can use it to generate new samples of experience. And all in all is also about creativity, because if I can generate things that are not only technical artifacts or sensory observation, but I might be willing to push things to the point in which I'm attempting to create art, create music, create picture, create paintings, and so on. So I trust I convinced you, or you probably were already convinced, that learning is about data. So data representation is fairly important. Understanding the nature of the data is fairly important in order to get the correct machine learning model in place. Okay, so we do have a very many different learning type of data, but let me try and schematize some big families. Okay, well, the first type of learning of data we might be operating on is vectorial data. It's the classical vector of numerical features. Okay, age, sex, profession of a person. So describing a patient in terms of its exam history, whatever. Okay. And vectorial data can be used in input to this model, can be used in output can be the output of this model. Fine. The point about vectorial data is that it's atomic. It's of course made of components, the various boxes of this vectorial data, but those components are in a flat relationship one another. Okay? There is a relationship between these two components. There is the same relationship between these two, okay, at least in terms of data representation. Then there is images. Images are slightly more complex than vectorial data. It looks like vectorial data generalized to the matrix world, but it's not like that, because the images have structure, because these pixels needs to be considered together more than this pixel needs to be considered together with this pixel, because there is geometrical structure, spatial structure in the information. And if we deny that spatial structure, we are not good at understanding what the content of an image. So that's where convolutional neural network hit the nice spot, because they recognize the importance of considering the local structure and increasing the more abstract levels of local structures that is underneath image data, and that needs to be considered if you want to be performing well on images. But as I said, we don't have time to do images today, so I will skip convolutional neural networks. And then there is structured data. Structured data push the idea of having information that has relationship inside it to the next level. Think about sequences. Sequences represent a sequence of observation, clearly, a sequence of data points. And those sequence of data points come in a sequence. So they have a complete ordering, okay, speaking computer science. They have a complete ordering. There exists a complete ordering between them. The fact that there exists a complete ordering between the observation means that we would like to represent that ordering also in the having that ordering represented also in the learning model, because that ordering means something for the predictive task, for characterizing the data. We know that this guy here somehow depends on the predecessor, and this guy here somehow might depend in a far away from the first element of the sequence. It might not depend on a future element in the sequence. Okay? Then there are trees. We can get more, and clearly examples of sequences are everywhere. DNA sequences, time series from sensor data, financial time series, name it. Okay? We can make structured data more complex by saying, you know what, I'm not interested in complete orders. I'm interested in representing partial orders. Well, then you have trees. Your question. Or is just the mic, yeah, probably on by.
It's just somebody that has a microphone.
Okay.
Oh, that's it. Ready.
Okay, good. So trees represent hierarchical knowledge. You start from a root, you decompose, and the root is the more abstract concept. And then from the root, you have the children of the roots, and the children of the roots are somehow might be two concepts that specialize the abstract content in the root, and the children of the root further specialize the information of their parents. So trees represent this kind of hierarchically structured information. And trees are everywhere as well. Consider natural language processing, parse trees. Consider artificial languages, abstract syntax trees. Consider biology. In biology, we might represent the mutations of cancerous cells with clonal trees, which represent the various population, how the various population of a metastatic cancer evolved from a mother cell into subpopulations, and that is a fairly detailed picture of the state of the poor patient under metastatic cancer. And you can push that further by assuming that there is no complete order, no complete nor partial ordering. Sorry. Okay. Good. But there are just items and relationship between items, and that's graphs, okay? Graphs don't impose any ordering between the components. Graphs are made of nodes, and nodes can have information associated to them, and then links that connect to nodes that represent relationship between those two entities. And I'm not spending much time now to explain this because tomorrow is going to be all about graphs. So let me skip it for the time being. And today, instead, we focus on sequential data, and that's the nature of sequential data. A sequence is a set of observation with an ordering between the observations, okay? The key thing is that the single element of the sequence are no longer from a statistical perspective, independently and identically distributed, because observation at time xt depends somehow on what has happened in the past. That's the point. So observation at time t is somehow dependent, statistically dependent from what you've seen before. Okay, and you would like that to be represented, that information to be captured by your learning model. That's why we use recurrent neural networks, because they can keep an history of the past, because that is akin with the nature of the data that we are trying to tackle here. And one thing we are going to be needing to address is the fact that different sequences, so different examples in my data set, will have different length. So my neural network will need to be able to cope with the fact that the input that I'm receiving changes across time. Okay? Good. So just to complete the thing, if you have ever been exposed to a machine learning course, you know that in machine learning, statistical learning theory tells you that you are very much interested in doing something that is learning to fit a function with generalization in mind, especially if we talk about supervised learning. Okay? Generalization means that your function fitter needs to work well not on the training data, on the data that you used to fit, but rather needs to fit well in future data that is coming to visit your predictive model in the future. And that's a strong change with respect to statistics. That means that whenever we are assessing the quality and the effectiveness of a machine learning model, we always assess its generalization capability, the ability to predict well on future data. That is why we always keep under control two things: the training error, so how well the model behaves on the data that is used to fit its parameters, and the validation error, for instance, that tells how it's a first proxy on how the model will behave in the future. That's a first proxy because whenever you do this kind of stuff, you try out many different learning models, and when you try many different learning models, you compare them. You compare them based on validation error, possibly, and you pick up the best one. And then if you want to understand how this model will be working in the future, you need yet other fresh data that are a proxy for future data that is different from the validation, that is different from the training. Otherwise, you get a biased estimate of the generalization performance of your model. That is called test data. Okay? And there are certain numbers of statistically inherited routines to perform this kind of generalization test. I'm not going into these details, otherwise you can spend a full day talking about that. So a machine learning model, just simply put, is a computational model with parameters, theta, and those parameters are learnable. Okay, learnable based on what? Based on training data. Okay. Training data is used to fit my model. The fitting of the model is driven often by a function that is called a cost function that tells how much the model is doing well or bad on the data. Okay, and that drives tells me the direction which I need to follow if I want to adjust the parameters of my model, basically, the cost function. Then what I need, again, for generalization is testing the model against some fresh data that is not being used to steer its parameters, in order to understand in a robust way how the model is going to be performing in the future. Okay, because training data is easy to be learned by heart. Okay, machine learning, and in particular neural networks. Neural networks are over-parameterized machine learning models, which work by some magic, because being over-parameterized, statistical learning theory tells us that they should be overfitting, but they don't for some reason. Well, you need to be very careful in assessing the fact that you're really learning some generalizable information, some generalizable knowledge, something that allows your model to predict well also on data that has not been used on training data, because neural networks are very good at learning by heart the training data. Okay? If you allow them. And when you learn things by heart, in machine learning, you say that you're overfitting. Overfitting is this area here in which my validation error departs strongly from the training error. The ideal soft spot in which I do want to operate is this one, in which validation error is near to the training error. Okay, is as low as possible and near to the training error. And training error, as you see, you can push it as low as possible. You just need to increase model complexity, where model complexity is another way of saying number of free parameters in my model, fitable parameters in my model. I just need to increase the complexity of my model if I want to bring down the training error. Okay, that doesn't mean that I'm increasing that I'm bettering my validation error. In fact, it's the other way around, unless we use techniques to control complexity, which are called regularization. Okay, which I'm going to be speaking in this part. Now, I've rushed it through, I don't know, in 20 minutes through fundamentals of this machine learning. If you have any questions, you're particularly silent.
Can you hear me?
Yeah.
Good morning.
Morning.
You talk about regularization.
Mm-hmm.
It is always useful. I'm saying that because I read some papers where the scientists were saying that in some cases regularization may not be good because it's another approximation.
Okay. I don't know whether they were saying it from a theoretical point of view or from a practical perspective. Let's say this. From when you say regularization, in your mind, you should picture penalization. Okay? So regularization is, in a way or another, independently of the reason why you're doing that, you do regularization for many reasons. Okay? But you do it to penalize a bad behavior in your model. Okay? And when you apply regularization, you are penalizing the model. So it means that you apply regularization to a predictive model, you are penalizing its predictive performance. Okay. But that penalization most of the times is useful to penalize its predictive performance on training, but increase the one on the validation, let's say, in generalization. Is it always necessary? No, sometimes it can be hampering the performance of the model, because if your model is, if you have configured your model, let's say, to be too little complex for the problem is trying to learn, okay? Then if you regularize a model that is already too constrained for the problem, then you're creating problems. Okay, you're not helping the model. You're just making it more difficult for the model to learn things. So from that perspective, it clearly introduces a penalization with respect to the objective that the model is intended to follow in predictive tasks. So yes, it's somehow making the task less clear to the model, and possibly also not only to the model in theoretical sense, but in theory also tells you that you can't let an overparameterized model play on training data, because that will overfit. So it tells you that you need to regularize. And there are, I'm going to be showing you examples in which regularization can really naturally out of theoretical concepts. Okay, so it's not that bad. I suggest that unless you find strong evidence that in that particular problem you should not be applying regularization, you do apply it, because in practice and in theory it works. I'm going to be showing a couple of examples of different types of regularization. Regularization really can be used for many things. It's not only to control model complexity, it's also to enforce properties into the model, properties of interpretability. It's also used to enforce structuring of the representation of the neural network more often. Okay, so it's really a useful tool.
Okay, thank you. Just for saying, I read the paper called Normalized Free Networks.
Okay.
Where the idea was just to clip clip the weight when they
okay.
pass some I can say some numbers. Okay.
Yeah, no, it's vector quantized neural network, but that's regularization. It's regularization as well. Whenever you're constraining the representation capabilities of your model, you're regularizing it. So
okay.
yeah, probably they were selling their stories. So when you read articles, you should also bear in mind that authors are desperately desperately trying to sell the story to the reviewers in order for the paper to get accepted. But you know, when you clip the weights, when you quantize the weights of a neural network, you're regularizing the model. In fact, there are models. I'm going to be showing you models in which you don't learn the weights, and that's an integral regularizer. Okay, so or you just learn some of the weights.
Thank you.
You're welcome. So let's start delving into these neural networks. And first question should be coming on your mind is, why using neural networks? Apart from the fact that there is that big fuzz around, a couple of things that are useful in practice, and apart from the theoretical interest into that, they are universal function approximators. Okay, they are Turing equivalent when you pick up the recurrent versions. Well, that's all theory. To the when the number of neurons is infinite, they are non-parametric. Non-parametric means that if you compare them with other machine learning models, where you need when the programmer needs to have a clear picture of the nature of the data that is fed to the learning model, neural networks don't need that much reasoning. They don't need much information about the family of distribution that have given rise to the data. They are non-parametric. They can basically approximate any distribution. Okay? It doesn't mean that they approximate it well unless you get the correct design choices. That's another thing. Learnability is different from the capability of approximating any possible distribution or function. Okay? But they simplify the application. They are scalable, mostly because their computation can often be performed in parallel, and much of it is performed in parallel, because it's heavily supported at software and hardware level, this parallelization by GPUs, TPUs, FPGAs, you name it. Okay, clusters, multi-core systems, whatever it is. So you can parallelize their computing. So very much useful when you have a large amount of data, when you have complex problems. Okay? And there is another thing. Current deep learning frameworks, neural network frameworks, allow for an easy Lego breaking. So you you build models by taking components, neural components, and joining them because they speak the shared language of differentiability. You put them all together. The only thing you need to be careful is that you put things together, the whole thing still remains differentiable, and then you're happy. You don't need to do anything else. Okay, then the automated differentiation engine underlying the deep learning frameworks does the job for you. Actually, sometimes you even don't care if they are not differentiable. Sometimes you really approximate the thing even with the non-differentiable components. But that's another advanced thing we won't talk today. There are also aspects you need to be careful of when you're considering neural networks, okay? When there are stringent interpretability or safety and security requirements, you need to be careful. Neural networks are based on metric concepts, so on metric spaces. So basically, they leverage the power of a continuous space to represent information in this possibly infinite high-dimensional space, which is beautiful, creates nice, smooth representation, but it also means that I can really handcraft some non-random noise that perturbs my representation, my information, in such a way that I can really fool the network into predicting something that it's different than the expected prediction. For instance, I can draw the sign that you see here, which looks like a stop sign to a human, what looks like a sports ball to a convolutional neural network that has been trained to predict stop signs. Okay. Why? Because I've adversarially attacked, it's called, that particular picture, and crafting with mathematical tools a picture that looks as much as possible a stop sign, but it's not recognized as such by the neural network. So whenever you put that thing on the top on a self-driving car with an autonomous driving support higher than 3, that becomes an history. That becomes quite an issue. Okay. You need to be careful in using them when you have sufficient prior knowledge available to tailor a parametric model. If you know the data generating distribution pretty well, you might go for a model that leverages that information, because your networks seldom do that. Okay. You need to be careful when you have little data, because these are over-parameterized models. So if you work on little data opposed to big data, they might not be working well, or you might need to heavily penalize them by regularization. So at that point, you're not really exploiting very much the power of neural network. Okay. And all in all, that's why you like neural networks, because there is a jungle of deep learning frameworks out there. Some are fundamental, some are derived on top of others, but they are very easy to use, most of them, and allow you to hit the ground running with neural networks just by following a couple of tutorials, and you're up and running with your convolutional neural network, okay, in some 10 minutes if you have Python skills. Or if you have JavaScript skills, for what matters, because there are JavaScript versions. These are all Pythons, but most of them have, some of them also have JavaScript versions. You of course have C versions, some have Java support, and so on. Python is the classical language of machine learning, but there's support for other languages as well. So what's the whole thing about neural networks? Neural networks are grown out of the biological neural metaphor, which simply put is a cell that receives inputs under the form of chemical compounds, accumulate those chemical compounds received through classical exchanges between cells by the dendritic dendrites, which are basically the input lines towards the neuron, which is this cellular component here. They accumulate these chemical compounds inside, and once these chemical compounds are in a certain concentration, what happens is that an electrical spike is created inside of the cell and runs in the output line of the cell, which is called the axon, and these electrical pulse reaches other neurons, which are connected to these other neurons by dendrites, of course. There, another chemical exchange happens, and again, so substances are accumulated, and eventually a new spike rises. Okay, so all in all, let's think about it. What a biological neuron really brutally does is accumulate inputs up to a certain point and then fires an output. Okay, so that's where the McCulloch-Pitts model. McCulloch-Pitts are a psychologist and a mathematician that in the 40s, 46, I think, came out with the first mathematical model of a neuron, thought their mathematical model of a neuron, and they said, okay, you know what? One interesting thing is that there was no biological model of a neuron yet. That came, biological knowledge about neurons came in the 60s with, McCulloch-Pitts. No, McCulloch-Pitts, I already said now. God. Yeah, they will come to my mind. They won the Nobel Prize for that. But it came in the 60s. McCulloch-Pitts came out with an intuition of the mathematical model of a neuron before the biological neuron, based on behavioral observations. And what they said is, you know what, a neuron is basically something. This is my neuron. The yellow thing is my neuron. Something that takes a certain number of inputs, which are numbers. Okay, each of the neurons is multiplied by a weight and summed up. So what this yellow thing is doing is summing over the inputs from 1 to m, okay, weighting the inputs by the corresponding weight. There is a number, okay? And that weight, that theta weight, is what I learned with my learning algorithm, okay? Then this sum here, which is a scalar, is passed, it's often called the net, is passed through a function f, which is called the activation function. This is what tells you when the number of chemical compounds has reached the critical threshold to fire out a spark, the electrical pulse in output, okay? And in fact, this guy here, who's Rosenblatt, in the first computational model of the neuron, really built a computational model of a neuron which was summing the inputs and had as an activation function a ramp, an EV side function, a step function. So accumulating input until a threshold theta b, okay, whenever the net was exceeding the threshold, as soon as the network was exceeding the threshold, the neuron was firing a 1 in output. Before that, was firing a 0 in output. So it was a binary neuron with a non-differentiable neuron, because this is a non-linear, this is a discontinuity in the activation function that leads to non-differentiability in that point. But still, in the early stages, that was fine. Okay, so that was the first model. The perceptron was basically a weighted summation of the input followed by a threshold function. Okay, then in the ages, people started introducing the logistic neuron, which is a softened version of the step function. It's a sigmoid function, okay, classical sigmoid function, and that outputs between 0 and 1, but all the numbers that you have in the middle, and saturates on the left-hand side and on the right-hand side. A lot of issues with it is differentiable. It has a very bad derivative though, because it has a very derivative that has a very low magnitude, which means that when you multiply a lot of the derivative, that fades out. That was one of the issues with training deep networks before it. It was due to the poor logistic sigmoid here. And then a certain number of other activation functions came out. Some of them thought specifically to deal with the fact that we would like to have functions that when activation functions that when I differentiate them, their derivative is something that is close to 1, because I want to be possibly 1, because I want to be multiplying a lot of derivatives when I have very deep networks. And just to give you a name, ReLU. Okay, rectified linear units are basically linear units with some sort of nonlinearity, which have the nice property of having a derivative that is 1 in the positive on the positive end of the net. So we built this computational neuron model out of this original biological intuition of what's a neuron, and out of that single neuron, then we built with time a multi-layer perceptron, specifically after we've learned how to build multi-stage, how to train multi-stage networks, because for quite some time, between the 50s and the 80s, we didn't really know very well how we could train a neural network with many layers. Why? Because a neural network with many layers, okay, this is a neural network with, these are the inputs of a neural network, first of all, okay? This is where you plug your data. The data enters your neural network here, and data comes out of your neural network here in the output layer, where you get the prediction of your neural network. Okay, so the diagnosis of a patient. The patient enters here, you get diagnosed here. The layer in the middle here, according to my biased view, is where you learn to encode raw information about the patient into something that is nicely organized, into a space that is d-dimensional. So the hidden layer, let me first explain this, first sneak peek. What the hidden layer is doing is taking an x vector, which is possibly a vector in an n-dimensional real space, okay? Not necessarily, okay, because some of the inputs might be categorical, some of the inputs might be ordinal, whatever. Let's say general case, it's an RM space. What the hidden layer is doing is taking this patient represented in this space where the information is noisy, possibly not well organized. This metric space is possibly not well organized, and transform it into a vector A in an RD space where D is the number of hidden neurons. And where this RD space, where I represent information, things are represented in a better way. Be aware that D is not necessarily smaller than N, okay? It's not that I'm just compressing information. Sometimes I'm even increasing the dimensionality of my representation. But the point is that by doing so, and creating a representation of the original input information that makes it easier to predict, that makes me better at predicting. That's the whole point about neural networks, okay? Learning that thing. And learning to create this A representation of input information means that what I'm doing, for instance, let's consider a supervised case, is that I'm confronting my predictions that are output here with some ground truth information available for the training data, computing the error, which is my cost function that describes how well I'm doing, but this error is computed here at the level of the yellow neurons. The point is that my network has parameters here, okay? So these parameters here are directly connected with the error, so updating them to better the error is straightforward. These parameters here are not directly connected with the error. I need to bring the error back to this neuron here in order to be able to update this parameter here. And that, okay, interesting. Something has happened to my screen. Okay, hopefully you still hear me. Yeah. And that process of bringing the error back to where it's needed to update the parameters is what is called the backpropagation. Okay, because I need to project back the error that is available only at the output layer in all the layer of my network, because in all the layer of my networks I do have a parameter which I want to adjust, and to adjust in such a way that the representation that I extract betters the capabilities of the model of being a good predictor. Okay, and it took some 20 years. Okay, if you ask where Verbos, Verbos is a guy who in his PhD thesis has proposed the backpropagation in the 70s, and actually 74, I think. It's not called backpropagation in this thesis, but yeah, it was already there, the solution, but it took another 8 years for 10 years for Hinton to publish the backpropagation paper, where it became really known as the solution to training multi-layer networks in the 80s. Now, what are the important things about neural network? Architecture, okay? When we speak about machine learning model, we talk about inductive bias. We talk about the fact that every machine learning model, by its design, is made more amenable to solve one problem over another. That's called the inductive bias, okay? So it has a bias towards some kind of task over another. So you would like to design your network, since a neural network is a machine learning model, to have an inductive bias, which makes it a good, let's say, model for the specific task. So how do I regulate the inductive bias of a neural network? I do it by taking appropriate design choices on the architecture. Okay, it means that the number of layers, the amount of neurons, weight sharing, activation functions, the regularization strategies that I use, the loss functions that I use, all this stuff, all these design choices are important. This is what a machine learning engineer learns to do. Pick up the right configuration, the right design choices when drafting a neural network-based solution to a problem, just like a programmer picks up the correct tools in order to develop a algorithmic-based solution, okay? In terms of data structures, in terms of languages, in terms of support to the language runtime support, and so on. So let's see how these architectural choices in some of the models we're going to be seeing are amenable for solving some specific problems, some specific tasks, for being good at some specific data types. Okay. All in all, this amounts to in modern neural network, it amounts to doing a nice import from Keras, and then you got all the layers that you'd like, all the solutions that you need, or I say Keras could be any other deep learning frameworks. Previously, it was all about handcrafting them, then deriving by hand all the update rules, because you had to differentiate the things by hand on the paper. Right now, these deep learning frameworks do the differentiation automatically for you. And that differentiation is there, because, as I said, we learn the weights of a model by gradient descent. So what we do is, as I told you, a neural network, just like other machine learning models, have a loss function. Call it E, call it I, call it L, whatever it is. It's a loss function. It's something that tells you how good you're doing, given your current setting of the parameters, given a set of training or validation data. Okay. Now, especially on training data, what you would like to do is check how well you're doing on your cost function for a specific sample of data, and then modify the weights of your network in such a way that your loss function, which is a cost function, is reduced. The direction of reduction of the loss function can be easily inferred by looking at the gradient of the loss function. So that's how you update your model parameters. So you take the old value of your model parameter and you change it in the direction, in the inverse direction of the gradient. It's inverse minus because it's you want to minimize. So if this is the gradient direction, the direction of increase of your loss function, you want to be getting to the bottom of it, to the minimum of your cost function. So to pick up the weight configuration that brings your neural network to the minimum of the empirical loss. It's an empirical loss. Why? Because I'm computing it not as an expectation of the original data generating distribution, but I'm computing it on single samples, on empirical samples of experience. So we're bringing this loss to the minimum in expectation, okay, with respect to the empirical sample.
Davide, can I ask you a question?
Yes, sure.
Okay, this is a great idea. It works. It is extremely simple, but it's also a very local point of view. And we know that in optimization, locality can be a curse. It can be a real problem. So I was wondering while I was studying these things, is there any approach to some more global way to deal with the loss?
That's a very good question, actually. A global optimization approach. There are people that are attempting at doing things using genetic algorithms in order to provide some form of more global view over the optimization process. Optimization processes are usually more, let's say, in neural networks are typically more local. Okay. In fact, that's where I had in my other slide. lots and lots of the work in this field is around getting your local optimization algorithm better and better by integrating more information about higher order derivatives, there's a lot of research about making the single learning steps for the single weights adaptive, because that regulates the schedule that you use to move in the surface of your error function. But global approaches, that's a theoretical question. Let's say there are works that are studying the global properties of stochastic gradient descent. Okay, but the optimization algorithm used in practice are all local. The only ones that I can think of that really depart a little bit from the locality assumption are those that leverage genetic algorithms, because they attempt at grasping this general information about the loss with this evolutionary approach. But I'm no expert in that, so I really can't say much further than that.
Okay. Thank you very much.
Thank you. So all in all, as Alberto said, the thing is that unfortunately the surface of the loss function is seldom like the one that I showed in the previous picture, and it's seldom also like this one. It's more like a mess, and it's a messy surface made of a lot of bumps, local optima, that you need to escape. That's why much of the work is about on these guys and their derivation, like Adam and so on, because they attempt to provide you with optimization algorithms that can escape reasonably well from local optima. And much of the state-of-the-art optimization algorithm are basically working around the fact of having a personalized learning, let's say learning rates, alphas in this picture, alphas here. Instead of having a single alpha for all the model, for all the parameters, having an alpha personalized through all the for all the parameters in such a way to regulate the speed of the single parameters update based on the local information, also considering the history of the updates of the parameters in such a way to be faster when it's possible to be faster for specific weights, and slower when it needs to be slower to reach convergence, because the problem is always that of attempting to find a trade-off between speed and stability in optimization algorithm. You want to be quick, but you don't want to overshoot the target. That's basically just like general optimization problems. And it's also about picking up the correct learning fashion. Okay, there is the classical stochastic approach, the sequential mode you do have, in which you update your weights after every sample. That's stochastic, fully stochastic gradient descent is about that. You see a sample, you feed it to your neural network, and neural network predicts some output for that input. You update the weights. New input, output, update the weights, and so on. Okay, that's fully stochastic, because everything depends, the gradient that you see depends on the specific empirical samples that you're seeing currently. Then there is the batch mode, in which you basically have a gradient which is the result of running the empirical expectation of the gradient on the whole training set. Beautiful, you get a single gradient, so you basically update your weights only at the end of the learning having seen all the data, but it's damn slow. Okay, it's really damn slow. While the first one leads to noisy direction of change because it's stochastic, the second one, it's damn slow, and it typically gets trapped everywhere. Okay, actually, there are theoretical studies that tell you that stochastic gradient descent, thanks to this noisy behavior, as a self-regularization, imposes regularization on the learning of the neural network. So actually, neural network really work also because of stochasticity of the gradient descent. Okay? Because the noise introduced by the stochastic gradient is a natural regularizer for the neural network, which has decently good properties for reaching the global optimum. This said, there are plenty of studies that tells that, and plenty of studies that demonstrate counterexamples to that. So it's still a very debated theme in the community. What is not debated is the fact that you probably, in practice, would like to be working in the middle between sequential and batch mode, the so-called mini batch, in which you get your training data, and instead of using a gradient on the full data or a sequence of stochastic gradient, you split it into smaller batches of data on which you compute an average gradient, and then you update for all the after every mini batch. So that smoothen slightly the gradient, because you have a gradient that is a little bit less stochastic. It's averaged on the mini batch, and it's more computationally effective than the stochastic gradient descent, because you basically keep the parameters fixed for all the patterns in a mini batch. Means that you can fit the mini batch in GPU and compute all these input patterns in parallel. With the stochastic gradient descent, you can't do it, because you change the weights that lead to a prediction after every pattern. So you can't parallelize. So mini batches are good for this reason. Okay, computational efficiency, smoothing of the gradient, averaging of the gradient, basically. Let's get to regularization. Regularization is about taking your cost function, your original cost function that is focusing on being good at predicting on training data, and perturbing it with the addition of a term. Okay, that term is a penalization term that typically penalizes the network for using too many things, where things can be either parameters. So my regularization term, what it can do is penalize the network if, in order to achieve an high accuracy on the loss, and it's the training loss because I'm using it to train, if it uses too many parameters. So classical thing, I add a term which is possibly the norm, the one norm of the weight matrix, okay, or the two norm of the weight matrix. I can even penalize an activation, and I'm going to be showing something about that. So penalizing of activation is penalizing a network for using too many neurons to encode information. Okay. And clearly what it introduces is lambda, which is the classical regularization which regulates the trade-off between being accurate and being using too many parameters. And that is a critical parameter, because if you pick it too big, too large, what you end up with is a network that cannot learn because it's too heavily regularized. If you take it too little, you end up in overfitting. How you pick it up? In model selection, by keeping a validation set in order to be able to pick up the best lambda parameter and then assess the ultimate performance of your model on some additional test data. And now we can go deeper, but possibly, I don't know whether you take a break, possibly you do so during this
Yeah, maybe a few minutes break can be useful. Before that, I was really puzzled by your comment on the penalization of the activation function. Can you elaborate on that? What is an intuition behind penalizing an activation function?
It's basically penalizing, if this is, let's call the activation of the hidden neuron. Let's say there is an hidden, only a single hidden layer, okay? So this is sum over the activation of the neurons in the hidden layer, okay? So this summation runs over the neurons, and then I penalize their absolute value, okay? So this is the activation of the hidden neuron in the hidden layer, okay? So what this is really imposing, this is an absolute value, is imposing a sparsity constraint. So if I add this term here to the loss, the network will be pushing the weights in such a way that not many neurons are active, because otherwise this second term will become high, and so this will increase the overall cost. And by this means, basically, the network learns to keep only the neurons that are very important for being good at this first part of the cost function on, and the rest off, if they don't support a good predictive performance. Because if you don't, basically the model can leverage the weights, for instance, to remember the full input pattern, even the noisy dimension of the input pattern. For instance, if you want to get rid of the noise in an input pattern, that is what we would like to use. You don't want the hidden neurons to waste some of their activation to encode the variation in the input data that are due to noise.
Right. Yeah, I see. Yeah, it's interesting. Actually, I was thinking that even a further direction would be some sort of activation in the non-linear part of the activation step.
Working on the activation functions, one needs to be careful. In fact, actually, there are regimes in which the activation function work well, other regimes in which they don't. And in fact, that is mostly something that you do at either initialization time, in which you need to be careful to position your weights in such a way that the activation function can work in the dynamical regime. Okay, if you have a sigmoid-like function, after my bad drawing, you don't want it to be starting there, because that's a very bad position. You have zero gradient here. You're never learning nicely. You want it to operate here.
Right.
Yeah, that's the dynamical range. And if you get the initialization of the weights wrong, you may end up here. That's why you do have things such as the Gloro initialization that provides you with some guarantees that you're operating here, at least at the beginning. And then there are things such as batch normalization. Batch normalization is something that you use also to avoid this kind of issues during training. The fact that the activation of early layer might get into a configuration in such that they are feeding layer L with layer L-1, and the activation of layer L-1 might induce layer L to operate in this region of the activation of the neuron, which is not good. So you use techniques to basically normalize the activation of layer L-1 to keep layer L to operate into the dynamic range.
I see.
That's where you want to be keeping your model.
You want to stay in the significant portion. That's right.
Exactly. And if you're going here, you really need to be getting there at the end of learning as a result of the fact that, very peculiar configuration. But otherwise, you would like to exploit this region, and this region in particular, which is where you have the non-linearities in the end.
Okay. If there are no more...
Yes. Penalty on activations is similar to dropping out some neurons?
Yeah, dropout is a regularization approach. It regularizes neural networks by making some of the neurons or some of the connection disappear during training time. So it's another way of making less weights available when training. So what you do with dropout is you basically draw a mask of binary, draw a binary mask every time you feed an input to a network, and you silence neuron based on the mask. So every neuron which has a 1 in the mask is basically shut off, silence it. Same thing can be applied to single connection. It doesn't matter. It's called drop connector. It's the same thing. And the intuition underlying that is that you're allowing less weights to be updated because you're silencing the network. So that's a network regularizer. There are actually a certain other numbers of methodological, theoretical properties underlying dropout. One thing is that you're obtaining a committee effect, because basically what you're doing, since you're changing all the time the connectivity of the network that you're using at training time dynamically, because you're shutting off different different neurons all the time, you're obtaining a committee effect. So your neural network is basically a committee of neural networks, because it changes all the time the structure. And we know that committee machines have a nicer performance over over a monolithic model in some conditions. Yes, but dropout is certainly a regularization technique. And again, underline it, there is the concept of constraining the number of weights that can be used, or the number of neurons that can be used. It forcefully shut down units or connections.
Can I make a question?
Yeah, go ahead.
I was wondering if there is any application for in practice for a stochastic gradient descent. I'm thinking some application for real time net where you have to recognize, for example, one image at each time.
Yeah, that's called continual learning. If I manage to get at a certain point in my presentation, well, I will be sampling from now onwards. But yes, if you're in an incremental scenario in which you would like to learn as you go, you certainly use stochastic gradient descent. If you are in a batch situation, the point is, if you have a batch of data already, so somebody has collected the data, maybe using fully stochastic gradient descent is not a more efficient and effective way. But of course, if your data comes in streams, so in an incremental fashion, then of course you have no choice, but either to, accumulate the data and then learn, or you learn as data comes with stochastic gradient descent, and that's what happens in continual learning, for instance. That's a good point.
I was thinking something about train the net in the same way that it will be used. So, for example, training with one sample at each time, because then it will be used one sample at each time.
Yeah, but that has no connection. I mean, the fact that it's used one sample at a time has no influence on how you train it. You're training one sample at a time anyway. But you expose the network one sample at a time. It's just how you compute the gradient after that.
Yes, for that reason, to have the maximum accuracy possible.
Yeah, but since you're not changing the network when you're predicting, it is not really placed within the same condition. It will be true if you want to have a characterization of the behavior of your network when in use, and when in use the network is being constantly trained, but it's not like that often. Often it's just prediction, and it doesn't change if you. I mean, the fact that you train it by stochastic gradient descent or by batch does not influence the way it's going to be predicting on the single sample.
Okay, so there is no real difference.
No. From that perspective, no.
Okay, thank you.
Great. So let's have a short break, and then we can start again. 5 minutes. Okay.
I just have another 60 slide. No worries.
That's fine. Wonderful. We have time.
Okay. I hope you had a nice and refreshing break. From now onwards, I'm going to be sampling, as I anticipated, some interesting concepts. And if you see something that is more interesting than other things, just let me know and I will stop on that. Otherwise, I will proceed in presenting some things that I feel that are interesting, that can provoke a little bit of discussion, okay? So, about going deeper. Well, deep neural networks. It's just neural networks with a lot of layers. It's not really like that, okay? Deep learning, as I anticipated, is much about learning good representations. So creating all the necessary methodology in the neural network field in order to be able to learn good representations of complex data and doing it efficiently and effectively. And one of the reasons why it's not that people haven't thought about deep learning for many years, it's just that it wasn't working, okay? So training neural networks with very many layers was not affordable for many years, for lack of data, for lack of computational resources, for numerical issues connected with the chain rule, basically, with the fact that you have with deep neural networks you have a long chain of multiplication of derivatives. If these derivatives are smaller than 1, okay, then that thing vanishes. So you get no gradient in the end. And so if you get no gradient, you get no learning. Or it can explode. Exploding gradients are easier to be tackled because you can bound the gradient. But if the gradient vanishes, you can't pre-normalize it. Okay. And so it took some time to understand what were the design choices to be taken. So what activation functions, what the topological features of the network need to be put in place in order to be able to train extra deep network. And let me tell you that there are out there neural networks that are as deep as hundreds of layers, okay? If you think about the ResNets have over 150 layers. So we really train very deep networks with appropriate tricks, okay? But the thing about deep learning is clearly not only just having a lot of layers just for the sake of having a lot of layers, is the fact that what we are attempting to do is that, okay, is attempting to reach an organization. As I told you, what we're doing in neural network is to transform an X into a series of intermediate representations, okay, A2, A3, okay. So if my X was original highly noisy pixel-based representation, the representation at level A1 of this noisy image is a representation in which we are highlighting the presence, for instance, of edges and blobs. At layer A2, we are highlighting the presence of object parts. At layer A3, we are highlighting the presence of specific objects. Okay, so that's what we would like to obtain. Why? Because then, if I attach a prediction layer on the top of these neurons that recognize the presence of objects, then it's easier to recognize objects than trying to do that from pixels, okay, which are a very low-level representation of information. And so, all in all, it's about representation learning. That's my own point today. And let me use autoencoders as a proof point for that. Autoencoders are a very old, just like with many things in deep learning, intuition, which is seemingly silly at the beginning. So it's a neural network whose job is to get in input X, okay, and spit in output X. So it's autoencoding because the prediction is identical to the input, which you would say, yeah, but this is a silly thing to do. Not really that silly. If you, for instance, constrain the representation that you find intermediately in the hidden layer to be limited with respect to the original input. And limited means that you can have, for instance, a number of hidden neurons that is definitely smaller than the number of the dimensionality of the input. That forces the neural network to compress the information from the input into fewer dimensions that are the most relevant one in order to be able to recreate that information in output in the most effective way. Why? Because basically my cost function will be how similar is the reconstructed X to the original X. Okay? So the network needs to learn how to compress the information in input in order to be able to reconstruct it. And one way you can obtain that is by having K definitely smaller than D, but there is another way by which you can do that, and we have seen it before. You can even have K to be considerably larger than D, but then what you do is, you enforce H to be sparsely active. Okay, so for instance, this is called the sparse autoencoder. This is the loss that measures how similar is the reconstruction to the original input. You have added a regularization term, which is exactly the regularization term that I wrote before, which is penalizing for using too many neurons. Okay, so the autoencoder needs to learn to compress input information into few neurons out of a population of possibly very many neurons. Okay, so in order to be able to encode into the hidden layer only the relevant changes in X that are useful to be reconstructed in output. Think about noise. Noise is something by definition that is unpredictable. Okay, so I want the network to not be wasting space, meaning parameters, to encode the noise, because the noise then it's not generalizable. I cannot predict the noise. I cannot predict how to add the noise in reconstruction, because noise by definition is unpredictable. Okay, so I don't want to be representing noise in my neural network. How I do that? By punishing the network for using too many neurons. Okay, and be aware that this network, this approach, okay, was built first in the 80s, and ideally people wanted to introduce it as a compression tool. So basically, they wanted to have the encoder part of the trained network on one side of a communication channel. Okay, we had the encoder on one side of the communication channel, send the compressed information in the communication channel, take the compressed information out of the communication channel, and with the decoder came out with the X. Okay, so that was the original intuition. Use it as a compression tool. It never succeeded as a compression tool. Okay, never ever. But I'm introducing it not as a compression tool, but for its intuition in representation learning. And in order to do that, let me introduce a different type of regularized autoencoder. It's an autoencoder that is regularized with noise. And be aware, noise is a strong regularizer. It's often used in neural networks. Okay, it's a very, very strong regularizer. How does it work? So basically, what I'm asking the denoising autoencoder is feeding. Once that I have, let's say, I have my input data X from the training set. I create a corrupted version of X that I called X hat. How do I corrupt it? With noise. So basically, I draw some random noise from a normal distribution and add it to the original X. Okay, so it's basically adding an epsilon noise and getting the corrupted X. Then I feed this in the autoencoder, and then I request the autoencoder to produce in output X. It's denoising. It's a denoising autoencoder because it receives in input a noisy version, and it spits in output a denoised representation of the input. Okay, and be aware, every time that I show it, since I show multiple times an input sample X when I'm training to the network, every time I draw a different noise vector. Okay. So the intuition is that the representation that I want to be learning inside of the autoencoder needs to be robust through some partial destruction of the input. And be aware, if you consider your input to be a vector in some space, this is your input X. What you're saying is that if you're drawing your noise from a Gaussian, for instance, okay, you're drawing your noise from a Gaussian with zero mean and fixed variance. What you're saying is that you're centering your Gaussian on the X vector, okay, and picking with the radius sigma here, okay, and you're picking up noisy version of X from this hyperbole, okay, and you're feeding the autoencoder with this noisy version. Okay? Seems like a nice intuition, nice trick. I make the autoencoder robust with respect to noise, fine. Well, that has first of all, it has a probabilistic interpretation, because what you're obtaining as a result of that is basically an approximation of is that your autoencoder is learning to approximate a distribution. It's learning to approximate a denoising distribution, because it's learning to approximate this denoising distribution, the distribution that, given this is the coder, okay, given the encoded information, H is the encoding, okay, of the noisy input. Okay, so this is the activation of the hidden layer for the noisy input. And for different axes, for the same axis, I will have different encodings, because every time I'm going to be using a different X. So I'm really learning not just a deterministic transformation from H to X, but something that looks like a distribution, because my H varies because of the fact that every time I pick up the X that is inputted to the network from to be slightly different because of the noise process. But the relevant thing, let me get to the point, is that actually you can demonstrate that the neural network is learning, that the noisy network encoder is learning something very interesting, which is a vector field. So in neural networks, we often, or basically always, make the assumption that we are reasoning with data, that our input data lies on a manifold. Okay. So the concept of a manifold probably is known to many of you, but for those who don't know it, it's in a very simplified form. So try not to faint if you're a mathematician. For a machine learning person, a manifold is basically a structure, a mathematical structure that is non-Euclidean. But if you look locally, so if you sit on it and you look around it, it looks Euclidean. So the word Earth is typically a manifold, because if we sit on the Earth, it looks like flat. Okay, when you're on the Earth, but we know that in practice is a sphere, or sort of spheric. Okay. That thing also means, from a machine learning perspective, it means that actually things that look to be in a certain dimensionality. Look at my camera now. If my data is coming from the surface of this cylinder, okay, I am representing it as three-dimensional data, okay, because it's on the surface of this cylinder. Okay. Actually, this data is on a manifold, because if I can take the cylinder and unfold it, okay, that looks like a plane. And actually, what look like three-dimensional data is in fact among these three-dimensional data, only two-dimensional variations that keep me on the manifold, on where the data is generated. Because if I move in a certain direction, I exit the manifold. Okay, if I exit the manifold, I'm basically departing from the area of the space where data is. Okay, so wherever I depart from the area where data is, I'm observing things that don't make sense, basically. Okay, so if I want to be characterizing the data, I would like to characterize the manifold. And so what I do to characterize the manifold is I understand only which direction of variation keeps me on the manifold, and are only those direction of variation that keep me on the sheet. Okay, these are the only direction of variations, and are only two. See, my three-dimensional data is only two direction of variation that keeps me on the manifold. So what we would like neural network to do, and in particular autoencoder to do, is to learn those two directional variations, which are the only meaningful two. Because if I keep moving on the manifold, I keep experiencing data. If I move off the manifold, okay, I don't read sensible data. So how does the noisy autoencoder connect with that? Well, think about it. So let's imagine that my data lies on this very simplified manifold. So it's ideally two-dimensional data because it's on a slide, but actually, if you look at it, it's on a line. So it's one-dimensional data. Okay, so it's two-dimensional data that comes from a manifold which is one-dimensional. Okay. So originally, my data is the red crosses, the points on the manifold. Okay, I don't know this manifold, but I'm doing it for visualization. Now, whenever I'm imposing some noise on the data in the noise and autoencoder, what I'm doing is taking the original data, consider this X, adding some noise C, okay, that knocks the data off the manifold, okay, possibly here. This is my current X hat, okay. What I'm then asking the neural network to do is to reconstruct the original data. So to reconstruct the original X, so to find the direction of projection of the knocked off data back onto the manifold, okay? So what really the noise in autoencoder is doing is learning a vector field, so a field of directions, okay? And those directions all get you to the manifold. Actually, what you're learning is a vector field of the tangent space to the manifold. So of all those gradients, of all those direction of movement, that take a point and bring it quickly towards the manifold. Okay, at least if you're doing the job good when you're learning. That's ideally what you're learning. Okay, so it's really a vector field that takes any point as quickly as possible towards the data generating distribution. And in fact, what you can show theoretically is that the noisy autoencoder is learning a score function. Basically, it's learning an approximation of the score function. So it's learning the gradient of the data generating distribution. Because the gradient of the data generating distribution tells you in which direction you increase the likelihood of a model, okay, of the data. And the direction in which you increase the likelihood of the data is the direction that brings you back on the manifold where data lies, is where the probability distribution of the data is higher. Okay, so this seemingly silly trick is actually doing something very interesting, because it's telling you that what you're learning is learning to present to represent data that is noisy and high-dimensional into its lower dimensional generating manifold, and learning in particular what direction of variation are useful, okay, because it keeps you on the manifold. Think about this graphical interpretation. That's a projection of the manifold for the digits, okay? Learning that by an autoencoder, you will learn the only good direction of variations are these ones, because are those that keep the data on the manifold. And possibly, if you move in one direction, in this direction here, what you're doing is, by moving on that direction, changing the orientation of your digit. If you move into this direction, possibly what you're learning the sides, to change the sides of your digit. So really capturing the direction of variation is understanding the data. Because if you capture the relevant direction of variations, then you can operate on those direction of variation and change the nature of the data. You can project the data on the manifold, training data on the manifold, and then start modifying it and obtain a new position on the manifold, decode it, and obtain new data, which is a 4 of different size than the original one. Okay. And also, by the way, you learn that you shouldn't be going in this direction, because if you go off the manifold, what you're doing is you're generating noise. You're creating, if you decode points of the manifold, what you get is noise, because it's no longer, you're no longer ensured that what you have is a meaningful information with respect to your training data. Okay. There are other ways of doing this, including the contractive autoencoder. We don't have time to check on this. So hopefully I've conveyed you. Do you have questions about this? Because this, I feel it's an interesting, a fairly interesting bit about deep learning models. The fact that what we're really attempting to do is characterize the manifold where the original data lies. Okay. In this high, complicated, complex, noisy space where we measure the data, the information actually lies on a lower dimensional representation, possibly smoother. We just need to find it. We just need to throw away those directional projections that are not relevant. And one way of doing that is that thing, well, it has been generalized to deep autoencoder. This is not really interesting. What I would like to show is that in time, we have generalized that concept to that of variational autoencoder, really considering the fact that what we would like to obtain by the encoder is not a probabilistic function that takes an x in input and encodes the x into a space z, let's call it z here. Okay, it's not a deterministic function, but rather the encoding is learning a probabilistic encoding, so a distribution that samples a z given an x, and a probabilistic decoding that given a z samples a reconstruction. Okay, that is what the variational autoencoder does. And the tricky thing about this variational autoencoder, training it, and the fact that it took some time in order to be able to train it, is that, remember, these things are trained by backpropagation, because the decoder and the encoder are neural networks. Backpropagation requires full differentiability. But if you are sampling here z, sampling is a non-differentiable operation. So whenever I can backpropagate through here, but when I get here, since z is sampled, I cannot backpropagate to the encoder. So that's a big problem. I can't train the encoder because it's non-differentiable. And the whole thing was solved by the so-called reparametrization trick, which is a smart way of being sampling, but not sampling in the chain of the differentiability. So basically what you do is you encode a neural network to generate the parameters of a Gaussian, like a mean and a variance. You have no sampling here. It's deterministic. You generate the mean and the variance. The sampling, you have it here. You have a sampler that works alongside your encoder that generates a vector Z1, that is drawn from a normal with zero mean and unitary variance. And then you rescale the sampled Z1 with the mean and variance predicted by the encoder. And then you feed this rescaled Z to the decoder. So in such a way that you have the sampling, but the sampling is in this side. Okay, and when you backpropagate here. You cannot backpropagate because there is the sampling, but you don't care because there are no parameters there. Here you can backpropagate because there is no sampling, so you can train your encoder. How you train your encoder? Well, there is one thing that comes from quite some theory that is called the theory that comes from generative models. It's called variational approximation, that tells you that basically what you're doing is you're training your neural network to, let's say, not maximize the likelihood of your data, but the lower bound. Okay, this lower bound is obtained somehow. I really need to skip this now, unless you want to know about it. But if you develop all these counts here, what you discover is that if your neural network, you call it Q, you can train that model by having your Q neural network match this prior distribution over your latent samples, okay? And your prior distribution over the latent samples is the mean, is the normal with zero mean and unitary variance. So you're going to be training your neural network Q to match this distribution in probability, basically by computing the Kullback-Leibler divergence between the distribution, the distribution Q and the prior distribution N. You can do that in closed form because both Q and P are Gaussian distribution, and we know the Kullback-Leibler divergence for how to compute it for Gaussians. Okay. Let me skip it through, but this is an evolution of that. This is just restating the same thing that I've shown before. It's an evolution of the noise in autoencoder, and in fact, you can use it to sample new data. This is data that is generated by starting from a phase projected in the hidden space of an autoencoder, and then I start moving on the hidden space of the encoder and sampling the coding points as I move on the hidden space of the encoder, because I have a decoder for the hidden space. And since I'm moving on the manifold, what I decode looks like original data. Okay, so if I train it on phase by decoding points on the hidden layer, on the manifold of the hidden space, I will be decoding phases. If I train it on cats, I will be decoding cats. Okay, and well, this is mostly it. You can use it in many ways. This is just to show that we've used it, for instance, to encode music, okay, into a latent space. So we have this variation autoencoder. Well, actually, it's an adversarial autoencoder, but similar ideas to encode music, okay, and then we can sample from the space, from the hidden space, new music, okay. Or you can study how the latent space organized with respect to some musical theories, and you see that what are the direction of variation of the latent space that connect with, for instance, the change in rhythm, with the change in the use of the bass, in certain notes in the bass, in certain notes of the guitar. So you can really gauge some of the dimension of the hidden space to change, for instance, ideally, the guitar riff of a song, or just by operating mathematically onto the dimensions of this latent space. I'm now really running out of time for the official timings, and I do have quite some other topics to present. On my side, I'm fairly open to go on for another 20 minutes. Then I have exams, but let me know if I should be stopping here. You tell me. I can go on for other 20 minutes.
Well, you can go on. You can go on. There is no real constraint from us. Whoever can stay will stay. Who cannot can always have it on the recorded material.
Okay. Okay. Good. So I just wanted to provide you some other pointers, but please interrupt me, because otherwise it's a soliloquy. I don't know if it's in English. It's the same word. But yeah, we use the same architecture also for reasoning on concepts. You can really use these latent spaces to encode, to start from images of, for instance, numbers, and then code the concept of number, of the number, of digit, really, of the 0, of the 1, of the 2 on the latent space, and then operate addition and multiplication in the latent space. So basically what you can do is supply your model with 2 pictures of a number, 2 pictures of another number, and then the model decodes the resulting addition operation or the resulting multiplication operation in pictures. Okay, so we do have a model who understands the pictures and the symbols underlying the pictures and the relations underline the pictures in their symbolic knowledge and creates pictures that are connected with the relation. Okay, so it understands the addition relation between figures and numbers to generate figures of resulting numbers that result from the operations. So there is a lot of work in this field that is fairly interesting. This was it about what I wanted to say on autoencoders, at least at the level of models that learn to represent information. I don't know whether you have any question, curiosity, whatever comes to your mind.
Yeah, is it possible to use an encoder, the Latin space of the encoder, as a conditional input for a GAN to generate something new? For example, for music or some paintings.
Yeah, the GAN is by definition already a sampler. Okay, so GAN and variational autoencoder are intimately related. They are both generative models. The difference between the two is that variational autoencoders learn basically data generating distribution. Okay, learn the distribution. GANs learn a sampling process of the data generating distribution. This has one effect, that GANs are more realistic, because what they are trained to do is to generate samples that are realistic with respect to the data generating distribution. They learn a sampling process of the distribution. Variational autoencoders are more explanatory, because what they learn is the data generating distribution. Then you sample the data generating distribution with classical sampling approaches. Okay, this makes them, let's say, less realistic in the samples often, if compared with the GANs. But you do have the data generating distribution. So once you have the data generating distribution, you can manipulate it. You can try to understand what are the conditional relationship between the items. So the two things are connected. But GANs don't need a variational autoencoder to generate things, because they learn how to generate things. It's their job to learn a sampling process without having to go through learning a distribution. They simplify the task. Yeah, go ahead.
We saw in the deep learning course the GANs, and we saw that they are fed with noise input or something conditioned.
Yeah.
So I was thinking that with an encoder, I can, for example, extract the patterns of an artist, and then try to generate new paintings with I can say that.
Okay. Yeah, that's interesting. Yeah, that can possibly be done, because basically what you're saying is that you're using the encoder as a generator distribution for the Zs from which the GAN starts to create the image. Yes, basically, typically the Zs from which the GAN starts from are drawn from a Gaussian. Okay, slightly high dimensional Gaussian, like 100 dimensions. So those Zs, you can easily draw them from an encoder. The thing you can't do, though, is to train the encoder end-to-end with the GAN, because there is sampling involved. Okay, so you need to pre-train it and then use it just as a distribution from which to sample. But that makes sense, yes.
Okay, thank you.
And the encoder, anyway, by the Kullback-Leibler divergence, is trying to behave like a Gaussian with zero mean and unitary variance. So it's possibly something very akin to what you will get from a GAN. Maybe people have already done it. I haven't checked it. I don't. Not to the extent of my knowledge, but you should be checking literature before. But it's a good idea. Okay. If you have no further curiosities, or on the generative part, let me just quickly draft the issue with the recurrent neural networks. Recurrent neural networks is what we use to deal with sequences, okay? So the basic idea is that what they do is compress information. They take information that enters into them sequentially, one item at a time, and each time I might be seeing a full vector, okay? And learn to compress it into one vector, okay, that summarizes all the information about the history that I've seen so far. And guess what this vector is? It's the vector of the activation of the neurons in the hidden layer. Only these neurons this time are going to be recurrent, because recurrency is needed to remember past inputs fed to the network. And this fact that I'm compressing a sequence into a fixed length vector is useful, because independently of how long the sequence it is, it will always end up into a vector of the same size, okay? Which makes it good, because then I can create all my predictive tasks on the top of this fixed length vector that encodes information of variable length sequences. That's the whole trick, okay? And there are different families of neural networks. The early ones were the fully adaptive ones, severely attacked by the gradient issues. Then there are the gated ones that attempt to solve the gradient issue by making the neuron more complicated, but able to learn longer time dependencies. And then there is the randomized approach, which attempts to solve the gradient issues by not learning. Okay, let me very quickly go through those so that you know that. This is let me skip it. It's all about telling you how a recurrent neural network works. A recurrent neural network works basically by having a neuron receiving input, the current input, and the output of itself and all the fellow neurons from the previous time step. Okay, so you see that this is the current output of a set of neurons in a layer. This is the output of the same set of neurons for the previous input of the sequence. Okay, so this is fed as an additional input to the neuron together with the current input that comes from the sequence and passed through a nonlinearity to generate the current output. The fact that I'm feeding myself my past input and the input from my fellow neurons allow me to keep a memory of the past, okay? Because inside h of t minus 1, there is h of t minus 1, so the previous input to the sequence, and also h of t minus 2. But inside of h of t minus 2, there is h of t minus x of t minus 2, and so on. So in h of t minus 1, there is information, fading information of all the past. Unfortunately, the fading is huge in these networks, in particular when there is a large distance between the input that I want to remember because it's so helpful for the task and when I'm using it for the task, okay? Due to the fact that I have to backpropagate through many copies of my recurrent weights in order to get there and make sure that that weight is increased in order to keep information about x1 in ht-1. The gradient fades, so it gets to 0, and I'm not able to train this weight here to recognize the effect of that x and how important it is for this state here in which I'm making the prediction. So, well, people basically study this fading of the gradient. Let me skip this. And what you discover is that the fading of the gradient is due to a long chain of multiplication in the gradient that is due to two factors, basically. The activation function that you use, because it's dependent on the derivative of the activation function, and the weight matrix that you have, because it's dependent on the nature of this weight matrix. Basically, what you discover if you study it, let me just make the long story short, is that fading of the gradient depends on the spectral radius, so it's a spectral property of a matrix, of the Jacobian of the derivative, of the Jacobian of the activation function, and of the spectral radius of the weights. Okay, so the best way would be to have this spectral radius, which is something that bounds these terms here, to be equal to 1, because then you have a long multiplication of ones, which does not create a fading of the gradient. Okay, and for that you need an activation function whose derivative is 1, and a weight matrix whose spectral radius is 1. This means, if you put together the two things, means linear function with weight 1. Okay, because the identity matrix is clearly a unitary matrix with the spectral gradient 1, spectral radius 1. The linear function is clearly a function that when you differentiate it as derivative 1. Okay. Unfortunately, that's a very dumb recurrence. Okay, it's this recurrence here. Okay, that's a very dumb recurrence because it allows uncontrolled update of the state. I need something that controls the update of my state. It controls what enters in my state. So basically, long short-term memory introduced gate to control what enters this linear recurrence. Okay, by placing an input gate that controls how much the input enters the linear recurrency, because otherwise this linear recurrency explodes basically. How much of the past of the linear recurrency enters the current update of the linear recurrency for the same reason, because otherwise you never forget. How much of the linear recurrency is shown to the outside world because you don't want to remember this thing re-enters myself and my neurons at the future. So you don't want to be flooding the other neurons with information that is unnecessary. So you just close the gate and you just output 0. So you make the neural model more complex in order to protect the sort of a linear recurrency, which is what you need in order to preserve the gradient. Actually, you're really altering the ideal condition by adding this forget gate, which introduces a dampening of the gradient, but it's in generally better. Okay. What I wanted to show you, apart from the applications, is that another approach to tackle the gradient issue is not learn at all. So the problem stems from the fact that when training the recurrent connection, my gradient fades. What if I don't train the recurrent connection? Okay. So basically, I've told you that deep learning is about architectural biases, so the topological biases of having a specific network architecture, plus the learning algorithm that change the weights. What I'm telling you now is that I want to get rid of the learning algorithms, at least part of it, and leverage as much as possible a good architectural bias. Okay, that's what reservoir computing does. Okay, reservoir computing is about having a recurrent neural network in which my recurrent neurons, okay, are initialized with random weights and kept fixed. So what I do is the W in weights and WR weights, the weights from the input layer and the weights, recurrent weights, are initialized and never change it. The only weights that I change are the W out weights, the weights that I use to produce the output. Here is called the readout, the outputs. So no problem, because I don't have to backpropagate. I really need to have to update only these ones. I don't have to backpropagate through here. No vanishing of the gradient. Okay. The reservoir node is a recurrent layer that is considerably different than the long short-term memory layer because it's made of a huge number of neurons. Consider that in reservoir computing, you easily have thousands and thousands of neurons, but they are sparsely connected. As you see here, each neuron receives input from a few neurons. There are even reservoirs that are doing like this, okay? But the recurrent neurons are connected into a chain, okay? And they share only a single weight. There is used one with positive and ones with negative value, okay? So you really create some recurrent layers with a very rich, let's say, amount of neurons, but very simple connectivity, very few weights, and none of them train. Why this thing does work in hell? Because what you're doing is projecting input information into a dynamic space, which is high dimensional. where differences cannot be noted in the original input space are exploded into a higher dimensional space in which a simple output reader can capture what is needed in order to be effective in the prediction task. And since it's a dynamical memory, you want this dynamical memory to have good properties, okay? And you cannot enforce those good properties with learning. You need to enforce them with initialization. So what you basically do is make sure that the spectral radius of the matrix, of the recurrent weights, is close to 1, because that's the edge of chaos, okay, in a dynamical system. That's where a dynamical system has the longest memory of the past, but still a fading memory of the past. So this dynamical system will forget about the past with some sort of a exponential schedule, but will have a long memory of the inputs that have been fed into the dynamical system. There is a whole body of research about characterizing this dynamical system in the best way, studying the Lyapunov coefficients, and studying them from the perspective of dynamical systems, because they are not trained. So you really want to initialize them in the best conditions. But apart from that, they are very easy to implement, very easy to train, because you only train the last part, and the last part can be trained not by gradient descent, but even in one shot, because they are linear systems. Okay, they are linear systems, so the weights can be found in one shot in closed form, and this makes them amenable to put the recurrent neural network into embedded devices, okay, into sensors. And that is something that we are doing, for instance, part of the project that I coordinate. We leverage, for instance, TensorFlow Lite. We modify it, we customize it to run learning embedded on devices. Okay, so that you can have a recurrent neural network that runs and learn continuously on a device, and you can't do that with a long-shortened memory. That's the cool thing, is that in order to implement your reservoir network, you just need a dynamical system. Why it's not? Oh. How you implement that dynamical system doesn't matter. So we do have reservoirs that are biological. They are really cell culture, and we read cell cultures because you just need to ensure that what you're reading has some sort of properties, but then from what is generated is not important. So you have an electrode feeding into cells, and then you have a readout reading those cells. And this is the reservoir of your recurrent neurons. Or you do have photonic devices. So your reservoir is a physical reservoir of photonic units. Okay? So this really leads the way to, on hardware, physical implementation of neural networks. And there is a whole bunch of research about neuromorphic, what's so-called neuromorphic hardware that runs neural network, not really runs on a general purpose processor, really runs a neural network. Okay, and you can even run it on wet tissues, okay, on biology. And that's a nice review if you're interested in seeing how this different physical implementation of reservoir computing work. Do you have questions about what I was chatting about now before I conclude?
Yes.
Go on.
Actually, I have two questions.
Yes.
The first is, how is built the reservoir layer? I mean, is there any other kind of technique that build the layer in that way, or is someone who decide after several tests that is the best possible configuration for the layer? And if this type of models are related with the graph neural networks?
Okay, so first thing, how do you, in general, you sample the connectivity of the reservoir. So you impose a sparsity, you decide a sparsity proportion, and you sample a layer of reservoir neurons according with that sparsity proportion. you do use sample more than one, because the architectural bias here is strong because you don't have learning. So you really generate multiple ones, you assess them in validation, and then you pick up the one that is best performing. Okay, there is some freedom. Some kind of topologies you might craft them. Sometimes it might be the programmer that crafts them. It's really left to the expertise of the people who's designing it. But the general approach is to randomly draw it, okay, and then normalize the weights in such a way that the spectral radius is a specific spectral radius. Connectivity with graph neural networks. Reservoir computing can be extended to deal with graph neural networks, and tomorrow I'm showing it to you. So be patient.
Okay, thank you.
You're welcome. Other questions before I conclude? Okay, I've probably abused already too much of your time. Just random thoughts. There are alternative ways of thinking about recurrent neural networks. For instance, separating the fact that you need a nonlinear mapping from the input to the output, from the fact that you need a memory to remember things about the past. And one thing that we did is to propose an architecture that separates these two things with a very powerful nonlinear mapping and a memory which is a linear memory, because linear recurrences keep the gradient going on forever. Okay, this is called the linear memory network. If you're interested, you find some references there, and we have generalized it also to multi-resolution memory. That's not important. The last thing I want to mention is about using stochastic gradient descent when learning continuously. The next generation of neural networks will be networks that learn continuously, that don't learn necessarily only on batch data. If you have batch data, learn on that, but you cannot retrain always on full data. You would like to be able to add new experiences to a trained model without to have to retrain it from scratch, and this is currently not the case. But it's the focus on continual or lifelong learning field. Basically, the issue there is that you can show that if you train continuously, you forget what you've learned previously. It's called stability plasticity dilemma, learning new things without forgetting your past skills. There is a whole bunch of research in doing that, and some of those impose regularization constraints that come back again, that impose stability on some weights in such a way that you don't forget about the past. Some other approaches creates a network that self-grows to encode new information and new tasks. Some other approach use memory replay. So you remember samples from the past, or actually you do distill synthetic samples that in one sample remember all the necessary thing about the past to be injected into the neural network when you keep learning. And that's one work that we are doing with my group. We are fairly active on this community. If you're interested, check out Continual AI and the library that we have recently released, which is Avalanche. If you're interested in the field, it will be interesting to check it out, because it's basically the most complete and the most advanced framework for doing continual learning, for enabling your neural network to learn continuously. Oh, I'm really done with this, and I apologize. People that take my lectures know that I'm always late with things, so too many slides.
That is fine. That is fine. Thank you very much. And we noticed that you have a lab exam now, so yes, you must go.
I need to go. Yes, sorry about that.
Okay, and okay, so let's meet tomorrow 9:30, and we will have your material on the website of the course.
Absolutely, exactly. Thank you. Thank you, and sorry for rushing out of the lecture now, but I make sure that we have proper talking time tomorrow.
Yeah, sure. Thank you.
Thank you. Goodbye.
Arrivederci.
Ciao, grazie.
Arrivederci, grazie.
Grazie.
Grazie, arrivederci.
A domani.